Hi, I'm Paul Dickman, and this is an introduction to Cox proportional hazards regression. So this is the second in a series of lectures on survival analysis targeted at students and researchers in biomedical sciences who don't have extensive training in statistics. Now, in the previous lecture, I went over an introduction to survival analysis, introduced the survivor function, the hazard function, and how to estimate and test them. This lecture will focus on modeling time to event data with a special focus on Cox regression. And since what we're modeling is the hazard, I'm going to do a recap of the hazard. The slides are available on my website, as is code for reproducing the analyses that I'm going to show you. I'm going to show you examples in R, but Stata and SAS code are also available, which should give the exact same results. So, the hazard is a rate. So I'm going to start with an introduction to rates. So this is a measure of change of one quantity per unit change per unit of another quantity. So, for example, we might have mortality rates, 0.5 deaths per 1,000 person years. Incidence rate, we might see as 14 cancers per 100,000 person years. So these are event rates, and they're calculated as number of events divided by time at risk, or person time at risk. Now, the hazard, this is just the generic term we use in survival analysis to describe the event rate. So person time, this is a measurement combining both persons and time, and it's used to aggregate the total population at risk. So, for example, if 5 people are followed for 1 year, then this is 5 person years. Or if 2 persons are followed for 2.5 years, then this is also 5 person years. So if 5 people are followed for 1 year and 1 person experiences cancer, then the incidence rate is 1 divided by 5. 1 cancer divided by 5 person years at risk. If 2 people are followed for 2.5 years, and then 1 of those experiences a cancer during that time, then the incidence rate is also 1 over 5, 0.2 cases per year. You still have 1 case from 5 person years. Now, when we're reporting, we change the units. So, for example, you'll typically see cancer incidences are reported per 100,000 person years. Now, we're going to be modeling the hazard. I introduced the hazard in the last lecture. I'm going to leave these slides here for completeness. You can look at them yourself, but the hazard is the instantaneous failure rate. So, conditional on surviving up to time t, or among those individuals who are alive and at risk at time t, the hazard at time t is the rate of failing in the next small instance. So here's the mathematics for that. Now, when we model survival data, our models often adjust for the time scale. So it's important to specify an appropriate time scale. Now, this concept of timescales is sort of confusing, so I'm going to give an example. So consider the following questions. What's the time? How old are you? And for how long have you lived at your current address? Now, these are all timescales. And the thing which distinguishes them is the time origin, which is when is time equal to 0? So, for what is the time? Well, the time origin is midnight. It resets every day. So, the time is what is the time since midnight? And we typically specify it in hours and minutes, are the units. How old are you? Well, every person has their own individual time origin, their date of birth. And we specify typically the number of years since date of birth. For how long have you lived at your current address? Well, the time origin is the date you moved into your current address. And the time scale would be time since current address. So we could do a survival analysis for how long do people live in their dwelling. So we would follow them up from the time they moved in until the time they left would be the event. So time always progresses in the same manner, but by choosing a different definition of the time origin, we can change the time scale. So what are some common time scales in medical research? Well, attained age is a common time scale. We typically might want to adjust for age, and the origin is birth. If calendar time is the time scale, we would have a fixed date. Time exposed, or time since first exposure, we might have time on study. Then the starting point, the origin, is entry into the study, or time since diagnosis is the time scale, the date of diagnosis is the time origin, and time on treatment, we would have the date of start of treatment as the time scale. Now, this concept is potentially still a little bit opaque. Hopefully, it will become more clear as we go through. But the reason I'm introducing it now is in the software, you will often see you need to specify the definition of the origin. So the take-home message, keep in mind that when modeling survival time, when modeling time to event data, we typically adjust for the confounding effect of the timescale, and we need to choose an appropriate timescale. Now, here is a graphical illustration of the survival times of 35 patients diagnosed with colon carcinoma on two timescales. So we have patients who are diagnosed from 1985 until the end of 1995, and they're followed up until the end of 1995. And in the last lecture, I said survival outcomes have two dimensions. There's the binary event indicator, and here the solid dots are those who died during follow-up, and then the open circles are those who were censored. So here, censoring occurred administratively at the end of 1995. Everyone who was still alive at the end of 1995, their survival time was censored. And then the other dimension of the survival outcome is for how long each individual is at risk. And here we've illustrated the survival experience of this cohort on the calendar time scale, but when we analyze it, we often convert to the time since diagnosis time scale. Now, the length of the lines and whether they ended in a event or a sensory remains the same, but we've ordered them in a different way. And this has implications for our analysis, because when we fit the survival model, the model looks at when an individual experiences the event, it compares the covariates of that individual to the covariates of the other individuals who are alive at the same time. So by changing the time scale, we change who else is at risk at the same time as when the individual experienced the event. Now here I'm getting very heavily into how the model is estimated, sort of too heavy for an introduction. But what I would like you to take home is that there is a concept of timescales. You do have to choose one, and the Cox model will adjust for your chosen timescale. Now, we're modeling the hazard function, and the hazard function can take a number of different forms. Well, in fact, an infinite number of forms. But some of these have particular names. So a bathtub-shaped hazard, well, this is appropriate in most human populations followed from birth. We have a slightly high infant mortality, then mortality sort of decreases, and then it starts to increase again in old age. A decreasing hazard, well, this is appropriate following the diagnosis of many types of cancer. Mortality is highest directly after diagnosis and then decreases the longer one survives. Or a constant hazard is not that common in medical science, although there are some applications, most notably cancers of the breast and prostate, where excess mortality due to the cancer is relatively constant over time. A constant excess hazard is more common in other applications, and we often say the constant hazard can be described by an exponential distribution, and I'll get to that later when I talk about parametric models, but we talk of this as being memoryless. The expected survival time for any individual is independent of how long the individual has survived so far. So if we think about again, what's the definition of the hazard? Well, among the individuals who have survived up to a given point in time, it is the rate of failure at that time. And a constant hazard means that your event rate is independent of how long you have already survived. So the exponential distribution has been used to model the time between goals in sporting events. Now, the probability or the rate at which goals are scored across a sporting event, it's not exactly constant, but it's close enough that people believe we can assume it's constant. The average time to winning a prize for a regular lotto player can be described by an exponential distribution. The probability or the rate at which you win a prize any given week is independent of how many times you've bought tickets in the past. Now, the Cox model, the most common model in medical applications of survival analysis, is not a parametric model. With the Cox model, we do not assume survival times follow any particular parametric distribution, but I'm going to start by introducing parametric survival models. So it is possible to assume that survival times follow a particular distribution, such as the exponential distribution, and we could then model the hazard as a function of one or more covariates. Now, the disadvantage of parametric survival models, because there's a mathematical relation between the survivor function and the hazard function, assuming the survival times follow a particular survival distribution implies that the hazard has a particular case. So assuming an exponential distribution for survival times implies a constant hazard. And a constant hazard may not be appropriate for our application in medical science. Now, we can have more flexible distributions. The most common one is the Weibull distribution. This has two parameters. And with the Weibull distribution, the hazard can be monotonically increasing or monotonically decreasing or constant. So monotonic just means effectively constantly. So we cannot have a turning point. The hazard cannot go up and then go down again in the Weibull distribution. So this is quite restrictive because we often see sort of hazards with turning points. Nevertheless, some parametric models have proved to be applicable in medical survival studies. Other distributions you might see are the log normal and the Gompertz, but parametric distributions are often not appropriate, and by far the most popular model in time to event applications in medical science is the Cox proportional hazards model. So, what assumptions do we make about the shape of the hazards in the Cox model? Well, we don't make any assumptions at all. The hazard function, or the baseline hazard, is allowed to vary freely. And what we estimate is ratios between the hazard functions for different covariate patterns. And the estimated hazard ratios are adjusted for the effective time, but the baseline hazard is not estimated when fitting the model. So let's look at an example. So this is patients diagnosed with colon carcinoma from 1984 to 1995. We have potential follow-up to the end of 1995, and we're going to censor everyone at 10 years. Outcome is death due to colon carcinoma, and the interest is in the effect of clinical stage at diagnosis, which are classified into distant metastases or not distant metastases. Now, this is not sensible from a clinical standpoint, but I wanted to have a binary exposure to start with, because binary exposures are easier to work with, and I wanted to have an example where proportional hazards was approximately appropriate. Now, you're taught that before fitting a statistical model, have a look at the data. So let's have a look at these data. And for a time to event study, the data are a function of time. So the hazard for each of our two exposure groups over time. So what we can see is the hazard here, which is the mortality rate, the cancer-specific mortality rate for those who did not have distant metastases at diagnosis, and the hazard for those who did have distant metastases. And I've showed the graph for the entire 20 years of follow-up, but we're only going to model the first 10 years. Well, how do we fit a model for this data? Or what do we want to take account of? Well, in our model, we need to specify how the outcome, which is the hazard, varies over a function of time, and we need to specify how the hazard depends on our exposure. And the assumption we make is that at any point in time, whatever the hazard is in this group, the dotted red line, the hazard in the other group is a fixed multiple. And we will estimate the hazard ratio, the ratio between these two curves. So that's an assumption that we make in the model for how the hazard depends on our exposure. Now, what assumption do we make about how the hazard depends on time? We make no assumption at all. So the hazard in this group can vary any way at all and is estimated from the data. The only restriction that we make is the pattern or the shape of the hazards has to be the same for each group, because there will be a fixed multiple between them. So this is the proportional hazards assumption. The two hazards are proportional. And one of the reasons why I've only modeled the first 10 years of follow-up is that the proportional hazards assumption, and we have to remember it's never true, it's an assumption, but it might be easier to make it approximately true during sort of the first 10 years of follow-up. And also, the first 10 years of follow-up is where most of the events are. This is where we're most interested. We could possibly even restrict at 5 years, because this is where the great majority of the events are. So we want to model for the hazard where we will assume that the hazards for the two groups are proportional. And this is what the Cox proportional hazards regression model is. So this is how we write it. So what we want the hazard as a function of time and as a function of explanatory variables x, and we write it as the baseline hazard, which is the hazard function for everybody who has covariance 0. So this is analogous to the intercept in other regression models, or the intercept in linear regression. In linear regression, the intercept term is the value of the outcome when everybody has covariance 0. Well, it's exactly the same here, except the intercept is a function of time. So if we look back at the graph, this dotted red line, this is conceptually the intercept. It's the value of the hazard function as a function of time for the unexposed. Then, what we have here is, according to the values of the covariance, we multiply the baseline hazard by a fixed amount. So we have a baseline hazard, and then we have some multipliers, which are the effects of the covariance. Now, we can also write it on the log scale. If we take the logarithm of both sides, then we have the log of the hazard, the log of the outcome, is equal to the log of the baseline hazard plus the covariant effects. So it turns out that the difference between the two log hazards is a constant beta, irrespective of t. So the two hazard functions are assumed to be parallel on the log scale or proportional on the original scale. And this relationship is important because when we assess the proportional hazards assumption, it's often easier to put the curves on the log scale and look for a difference. So, the Cox model assumes that the two hazards are parallel on a log scale. So, here is a graph of the empirical hazards, or the hazards estimated from data. Now, does it look like there's a constant difference between these curves within the first 10 years? Now, there's not a constant difference. These curves are not perfectly parallel, but they don't have to be perfectly parallel. They just have to be close enough that we're willing to assume that there is proportional hazards. And here I would say I would be very happy to assume proportional hazards. And the concept of proportional hazards, how to test for it, how to relax it if it doesn't exist, that will be the content of another lecture. So, let's fit the model. So, firstly, I'm just going to do a little bit of data transformation. I'm going to create an indicator variable for distance stage. I'm going to create an indicator variable, which is dead due to cancer, and then I'm going to fit the model. So we have our survival object, which has the two dimensions of our survival outcome. We have the time at risk, and we have the binary event indicator, and then we apply the Cox pH function to our survival object, and we have one explanatory variable here, which is distant metastases, yes or no. And what we get from the model, we get our regression coefficient, which is a log hazard ratio, and we get the exponentiated regression coefficient, which is the hazard ratio. So much like logistic regression, if you're familiar with that, the regression coefficient is a log odds ratio in logistic regression, and then you exponentiate it to get an odds ratio. Here, the coefficient is a log hazard ratio. We exponentiate it to get the hazard ratio. So what's the interpretation of this? Well, patients with distant metastases at diagnosis have 5.28 times higher mortality than patients who do not have distant metastases at diagnosis, and it's assumed that they have this 5 times higher mortality at each and every point of follow-up. And we have a test. Is the hazard ratio different from 1? And we reject the null hypothesis. So there's very strong evidence that mortality is different between those with and without distant metastases. Well, this is a not clinically realistic model. This is for illustrating sort of survival analysis, but we're going to build it up a little bit and then fit another model later, which is more clinically realistic. But what would happen if we wanted to adjust for another factor? But before getting to that, I mentioned the Cox model. It estimates the hazard ratios, but it doesn't estimate the hazard functions. But after fitting the model, we can retrieve an estimate of the hazards from the fitted model. And so here we have the two fitted hazards. And we could compare these to the empirical hazards, the one estimated from the data without modeling, as a sort of a way of assessing the goodness of fit. So here we have the two fitted hazards, and these lines will be proportional. Or if we plot these on the log scale, there should be a constant difference between these curves. Now, what if we want to adjust for other factors? Well, it's the same as other regression models. We just put the other factors in the model. Now, I'm going to keep it really simple. I'm going to adjust for age, classify it into two groups: greater than or equal to 75 years at diagnosis, or less than 75 at diagnosis. Well, now we get estimated hazard ratios for the effect of stage, which is now adjusted for age. We also get a hazard ratio for age, which is adjusted for stage. And we see patients who were older than 75 had a 64% higher rate of dying due to the cancer than those who were less than 75. And what does our fitted model look like now? Well, we now have our model considers there to be 4 classes of patients, or 4 groups of patients. There are 4 combinations of the binary stage and the binary age. So our model will assume that there is a hazard function for each of these, and the hazards are proportional. So here are the 4 hazards, and you can see that there is a turning point in the hazard. So the parametric models would not be able to capture this. Okay, The rest of the slides is the proportional hazards model in more detail. I'm going to stop the lecture there, and I'll let you read through these slides at your leisure. It's just a more in-depth mathematical description of the model and some more examples. So I'll stop the lecture there, but the slides are on the web page for you to read. Thank you.